All right, guys, so I'll make this a little bit bigger. Listen up. Should have yours out in front of you. All right, so I'm not going to, you can see the review answers, but once we have, past the first study guide, there's always a couple review questions that anywhere earlier. You can just look at the answers to those and make sure you got them right. And they go down to where speed and velocity is. So mainly, as long as we remember which one's a scalar and which one's a vector and the specifics of how we calculate them with the equation. They're almost the same equation, right? Almost. But they differ. If I want to calculate speed, what do I divide by time? Again, distance. If I want to calculate velocity, what do I divide by time? Yeah, displacement. And keep remembering that in the right scenario, distance and displacement could be practically the same thing, at least the same magnitude, right? And therefore, for that same reason, speed and velocity could be pretty much the same thing, at least their magnitude, as long as we never change what? Direction, all right? If a directional change happens in the time interval, then those things will be totally different magnitudes. Question? Well, basically just to define it through the definition itself. I kind of probably see what you're getting at, because like the fact that it's a vector and it takes into account, it only cares about beginning to end, all right? It only cares about, like we say, from where you started to where you ended and how fast it took to do that, all right? So without worrying about, with worrying about the fact that you changed direction and got there. Not the whole way along the way, though, like speed, basically. Let's put it this way, though, since you kind of asked that question. When we move forward, usually we do care about just like from one point to when we change direction. So if we do have a situation where there's several segments to the problem, let's say something goes this way, then that way, then that way, we usually will not figure out as a whole trip. We'll usually figure out stuff per segment, for the segments that didn't change direction, all right? And in those ones, the most important thing is to realize with studying this now is that if we do it segment by segment that didn't change direction, then speed and velocity are pretty much the same thing. The only technical difference then is that velocity still should, on its magnitude, include what? Something that signifies direction, right? All right. So just one big thing why we start the year with this stuff is because we don't want you to think that speed and velocity are the same thing. They have technical differences that we're studying now. However, most of the time we apply it, they seem like the same thing because of what I said. But if we don't study this now, that might pull you into thinking they're always the same thing. So that's why we go over this basically day one. Okay? Same with distance and displacement. But you'll see as the year goes on when we start applying more and more math that we typically, if something has segmented motion, we just figure out stuff one segment at a time, more than likely. Okay? So anyways, as we go through this, there's some similar questions like the one before, but we're thinking speed velocity now as opposed to distance and displacement, so that's all still kind of built into all this. So in number 3, suppose you are considering 3 different paths, A, B, and C, between the same 2 locations. Now, those 2 dots are the same distance apart in all locations. And that sounds like along which path would you have to move with the greatest speed to arrive at the destination in the same amount of time? So path C is the right one. Why? Okay. Right. What it's saying is we're all starting here, the starting line, right? The starting point. We're all getting to here in the same amount of time. But if you just use a little common sense and think about it, if that's happening, this guy went a lot further. If we stretch that out in a straight line, he went like this far, right? Or the other guys went this far. Well, that all happened at the same time. He had to move faster. Make sense? So your explanation just has to say something along those lines. Number 4, true and false. Is it possible for an object to move for 10 seconds at a high speed and end up with an average velocity of 0? This is very similar to a question we had in the prior one. It's true again, like the other one was true on the prior study guide. Why? Why could we move around for whatever amount of time and still have a velocity of 0? Yes? Right, because as we said, and on the next page at the top, the calculation for low velocity is displacement over time, right? And we now hopefully know that a displacement, when we come back to where we started, is 0. 0 divided by any amount of time is still 0. Doesn't matter the time, really. Velocity of 0. Moving along to number 6. Suppose that you run for 10 seconds along these 3 paths. Rank them from lowest average speed to greatest average speed. And for the first one, the lowest average speed would be B. If we look, all these paths takes 10 seconds. That's the key to understanding, and it should be simple after that. If all these paths are 10 seconds, then this person's got to be the slowest because he moved the least distance per that time, right? We don't have numbers, but we could easily see that that would be the lowest distance, the lowest magnitude distance, right? And then this one would be in the middle. And if this guy went all over the place in still 10 seconds, like these guys moved that, that's got to be the fastest because he traveled the furthest distance. It's distance divided by time, BCA. Be careful with the next one. Lowest average velocity is going to be A. Why? Why is that the smallest velocity now? That was the greatest speed. But why is that the smallest velocity in this particular instance, Chuck? He goes back to the same place, so that one's 0, right? Because it's velocity displacement over time. Then B and C tie on this one for the next ones. Why? Yes? Right, same displacement, right? They start at the same place, end at the same place. Velocity is displacement over time, so therefore those ones tie. Any questions on anything on the front? All right, going on to the back, just some calculations using those 2 basic formulas. Let me say something moving forward. Whether this makes sense or not, it doesn't really matter. It's just the way it is. Moving forward, past this, especially when we get to the textbook and more problems, when we use formulas to find average speed or average velocity, we always call it V equals D over T, even if it's speed. Here's the thing. You just have to know from this point on that if it's speed, you're technically going distance over time. And if it's displacement or it's velocity, you're doing displacement over time. We're still going to call it V equals D over T all the time. All right? But as I said earlier, explained earlier in this class period, most of the time we're going to be dealing with situations where we just went boom like that. So the distance and displacement magnitudes are going to be the same anyway. Okay? One other thing before I go over these, something real important about these formulas, the fact that they're averages. Remember, what is the only case, as we went over yesterday, what are tell me a situation where these could be better than average, only if you knew what. If you don't know this some way, shape, or form, you can't say that calculating like this is any better than an average quantity. What did we say yesterday? Only if we knew the thing was moving how. What's that? Oh, a radar gun took instantaneous velocity. We use that like to ask ways you could get something's velocity. But you're thinking in the right frame, but yes. Right, if they're going at a constant rate. All right? So how could you tell something's going out at a constant rate? You either have to be straight up told. A lot of times problems will say, in the future when this really matters, it'll say moving constant. You can't assume something's moving constant. It either has to tell you or you had to have been there to witness it happen. You know, or in a lab you set up something so it went constant and you set it that way, so therefore you know it. You can never assume something's constant. Therefore, if you use these equations, at best, they're averages for the trip. Yeah. Okay, but that would be just like me telling you, we're going to get to that very soon. Hopefully after next week, we get into motion graphing. And from graphs and data, if we know our mathematical relationships, which we'll learn, then we can tell if something's constant from a graph, from data, yeah. That could happen. Then we treat it almost like, I don't know if you're familiar with the term piecewise functions. We retreat, and this kind of goes back to what I said earlier today. We usually will just take the piece that it was doing this for and look at that separate from the piece that it changed for. And we'll like break it up into almost like different situations, different problems, even if it's all happened in one interval. You'll see it. It'll make more sense in about 2 weeks, a week and a half or so. All right. Anyways, So with all that in mind, hopefully these are pretty easy. Just watch your units all the time. They're throwing in some things here, just little things you could overlook if you're not reading carefully. Okay? Oh, and by the way, earlier this week or last week, whenever, we basically reviewed the metric system, right? Once we get past this intro stuff, you'll rarely see English standard units in here again. They use them early on, basically because you guys are familiar with them. But as we get moving further and further into the year, we'll almost never see English standard units because we see miles here, right? So this is one of the few times early on that we'll see miles because it's a standard unit. As we go on, it'll be pretty much all metric. All right, so this should be a familiar looking diagram. This is your house. This is your friend's house. Just like the one for distance displacement, we know it's 3 miles apart. And it tells us that you run first from here to here in 30 minutes. Then you walk back, and it takes an hour. So we need the total time, and it wants it in miles per hour. So they gave you at least easy numbers. You didn't have to do a math conversion, just a mental one. 1 hour and 30 minutes would be the same as 1.5 hours, right? So all we got to do is take for average speed, the total distance, which is how much? 6, there and back 6, and then divide that by the 1.5 total hours, and we get 4 miles per hour. But again, that is at best, as far as we know, average. Because did it say anything about like going constant? No, as a matter of fact, for the whole trip, we absolutely did not go constant. We ran for part of it and walked for part of it. And who knows, even when we were walking, maybe we walked a little faster, a little slower, right? So at best, that's just an average for the whole trip, 4 miles per hour. Average velocity, though, this one's really simple as long as you know what you're doing. It's what? 0, because we came back to where we started. And as I said yesterday, for any vector that has a magnitude of 0, then you don't have to put a direction on it because it wouldn't make sense to. If it's 0, it didn't go anywhere, right? It didn't go in any direction. If you have a non-zero velocity, then you better have like east, west, or whatever the directional stuff we're using. All right. This situation, similar to yesterday's as well, calculate, all right, before we get to that, the question. Each leg of the back and forth motion takes a minute. From A to B takes a minute, B to C, C to D, totaling 3 minutes. So remembering that and remembering stuff about the distance and displacement, it tells us to calculate the average speed and the average velocity in meters per minute. That's what it's going to come out to be. This whole number line, distance-wise, position-wise, is in meters, right? And these are all in minutes, so there's no conversions necessary, but always consider that. So for average speed, we need the total distance, right? As we answered in the study guide the prior day, the total distance was 360 meters. If we calculate it correctly, simply divided by 3 minutes, and we got 120 meters per minute. And the velocity, though, remember the velocity cares about the displacement, where we started here to where we ended here, which is 120 meters east, divided by 3 minutes. That means the average velocity is 40 meters per minute east. So hopefully those are pretty simple. Any questions on that? Okay. I will post these answers when we finish the last page. Remember, we're skipping this one. I'm just going to say one last little thing just to remember some stuff from yesterday. We don't formally do any math in here regarding instantaneous stuff unless we know it's going constant. Because again, if it's going constant, it's still the other equations, right? The simple one. But if we had something not going constant and we wanted to do some math to figure out at any given instant what it was going, we can't do it in here. What kind of math did I said takes care of that? Karis? Calculus. Calculus involves with changing rates at any given instance. This is not a calc-based course, so we'll make notes of it. This is where you would use it, but we're not going to be required to use it. We're going to see even more importantly graphically. All this stuff. And this is probably kind of different since we just threw these equations at you. Once we get to motion graphing after next week, you're going to see these equations didn't come out of thin air. We're going to use basic math we all know to actually figure out where these equations came from. Right now, we're just telling them to you. That's all year, at some point, any equations we give you, if we don't prove them right away, at some point we will. And a lot of them get proved with graphing. All right, but back to the quick instantaneous thing. We said something like radar guns and speedometers are devices that could take instantaneous speeds and velocities that could help us do that. But the math behind it's calculus. All right, so flip into the last page. I don't want to use the key for this one. Actually, I want to get a squid. Open up, if you don't have it in front of you, your same thing in squid and go to the 4th page. That same study guide. Okay, so all I want you guys to do right now, if you get stuck, do the best you can. We're going to go over it before the end of the theory. What time does this one end? 30 what? 36? All right, I'll give you about till 26 to get as far as you can on these problems. They're just using those formulas again. But be careful, especially with units. Pay attention closely. And in 12 minutes, whether you're done or not, we're going to go over the solutions, okay? Try to get them done by the end of the theory. Be careful. In some of them, sometimes you're given information you don't need. Sometimes there's numbers that are irrelevant. I'll never give you guys a problem that's unsolvable, but I will give you guys problems that have more than enough information. Not all numbers always get used. Sometimes you got to sort through what are you finding, what matters, and some of the information is going to be irrelevant to what it's asking. So be careful with that. There's not tons of work to these, but always start getting in the habit of any math calculation always showing as much work as possible, even if it's simple and elementary. I don't know if I said this yet, but even if I did. Final answers in here. Never fractions. Always give me decimals. And if it's a long decimal, I always said round to 1 or 2 decimal places, right? So keep that in mind. We don't want fractions as answers. This is another little note, guys. Remember, you could just abbreviate both of those equations into V equals D over T. But just, of course, if you're finding speed, use distance. If you're finding velocity, make that displacement. It could be the same thing if there was never a change in direction. You may have to rearrange this equation algebraically. We're all well past algebra 1 in here. For an equation this simple, I would expect I shouldn't have to show you how to do that. Now, we will get into more complex equations that we'll go through lessons on rearranging when they get a little more complicated. But a 3-variable equation, this is going to be as simple as you can get. You should be able to solve for any variable as necessary. So, did you do it fast? Yeah. Okay, go ahead. if you need a calculator, there should be one you could use on your Chromebook. Oh, I made a mistake there. About 5 more minutes. Don't worry if you don't get completely done, but I'm going to stop you there. We're ready to start going over. one more minute and we'll go over. Done or not, let's start going over them. We'll finish them together getting the full way through. So in number 11, 30 years ago, police would check a highway for speeders by sending a helicopter up in the air and observing the time it would take for the car to travel between two wide lines placed a tenth of a mile apart. Well, this still works. Speed traps that don't use radar guns, we all see when we drive around the two lines. And the two lines are close enough together that if you get caught through the calculation of speeding by basically using this equation, they're close enough together that you're going too fast. All right, in that. Is it as good as a radar gun? No, but for some weird rules, I don't know if it's just Pennsylvania, you can't use a radar gun unless you're a state police officer, I think it is, or there's some weird rules on what roads you could use them on, what you can't. That's why sometimes the speed traps are the lines. All right, but there was a time before radar guns where that was the only way to do it. All right, but it's based on the simple equation. So it tells us that the wide lines are placed a tenth of a mile apart. On one occasion, a car was observed to take 7.2 seconds to travel this distance. How much time did it take the car to travel the distance in hours? So it just asks us for a conversion, but conversion, I told you the other day, you need to know. How many seconds are in an hour? What's that? 3,600. So first thing we do is got to convert that. Even if it didn't ask us to do this in Part A and only asked Part B, we would have known we had to, because what does Part B ask? What units do we want? Miles per hour, and we weren't in hours, right? So it's kind of holding your hand through this one, but a lot of times it's not going to do that in the future. If something wants something, you got to know to convert if it's not in that unit. So we convert and just do the fact that we now know in 1 hour there's 3,600 seconds. Seconds would cancel top bottom. Run the math, which is essentially 7.2 times 1 divided by 3,600. And it comes out to exactly 0.002 hours. Now, I told you if it's not a nice number, around to 1 or 2 decimal places, but there are exceptions to that, and this is one of them. If I rounded to 1 or 2 decimal places on a number like this in particular, it would say 0 seconds, wouldn't it? So if 1 or 2 decimal places does not have non-zero numbers, then you do have to go further, okay? You do have to go further. So maybe we should say round to 1 or 2 non-zero decimal places, okay? And that comes out exactly in your calculator, it's 0.002. So we got that done. That takes care of Part A. We good with that one? All right, we use that answer in Part B. It wants us to know the speed of the car in miles per hour. When we need the distance, it's odd that it gave it as a fraction here, but we should know 1/10 is 0.1, right? So 0.1 miles. I'm going to write mi for mile, otherwise we might confuse it with what? Meter, okay? So 0.1, and it's once the average speed, and we were just given the distance. There's not even a displacement to consider, so it's going to be 0.1 divided by 0.002. What did you get? Exactly 50? Yeah. And that would be 50 miles per hour. No direction needed on it, because speed is a scalar, right? Hopefully should be pretty simple. As simple as these equations are, they're very important. All through the year, we might use V equals D over T if it's a place we could, if it's helpful for us. All right, moving along. We got the fastest trains are magnetically levitated above rails to avoid friction. The fastest trains travel about 155 miles in a half an hour. What's their average speed in miles per hour? So again, the D is simply, should be all obvious here. Nothing tricky in this one either. 155 miles, half an hour is 0.5 hours, right? So the speed is going to be 155 over 0.5. What do we get when we run those numbers? Go ahead, Chris. 210? Oh, yeah, 310 miles per hour. So no unit change there. That's about as basic of a problem as we could get. We all good with that? All right, now we'll get into some that might have some junk information. So read through it, pick out what matters, okay? In 1960, U.S. Air Force Captain Joseph Kittinger broke the record for both the fastest and the longest skydive. He fell an amazing 19.5 miles. Cool facts, there's almost no air at that altitude, and he said it's almost like he didn't feel like he was falling because there was no whistling from the wind or movement of his clothing through the air. We'll talk, that's actually explaining free fall, and that's a topic we get into fairly soon. The temperature at that altitude was 36 degrees. Obviously, that doesn't matter. We are talking about nothing with temperature here, right? So there's a piece of information that totally doesn't matter. His average speed, this probably matters, is 4 miles per hour. Just remember, whether it's speed or velocity, we signify it as this and just consider whatever. I think all these were speed, weren't they? How much time did the dive last for? So how before we find time, what other piece of information do we need to know? And they gave it to us. What else did they give us that was important? Or somebody else? Charlie. The distance, and that was up in top 19.5 miles. Now, obviously, we just got to rearrange the equation. If I solve V equal D over T for T, before I plug in numbers, I would flip it around algebraically, and it would become what? T equals what? Without numbers, variables. Tell me. Say that again? Now, be careful. Look at this. The original formula, let me give myself some more room, maybe off to the side here, okay? So, V equals D over T. So, essentially, you would have to multiply T to this side and divide V to that side, right? Or in other words, you're flip-flopping V and T, aren't you? All right? So, make sure we got algebra right. So, that would be T equals D over V. All right? And that would be, I'm running out of room here, but that's going to be 19.5 divided by 254. That's a little, let me zoom in there to get some more room here. And 19.5 divided by 254 looks like it's, if I round to 2 decimal places, I'm getting 0.08. Anybody else get that? Or 0.076 if you win another one? Yes? Okay. 0.08, or if I did go to 2 non-zero ones, 0.07, actually 0.077 if I did correct rounding. So I'll write the final answer here since I ran out of room over there. 0.077. What's the units on my answer? Yes. Careful. Yes. Hours, because we just found time, right? Time is just in hours. V is in miles per hour. That's not what we found. Yes. It would be okay. Here's what matters. You don't have to convert unless it tells you it wants a specific unit. You could leave it in whatever it comes out in. But in reality, if we were using this for a specific purpose, we would probably want to, because how often do you hear 0.077 hours, right? Usually when we get fractions of an hour, we either convert to minutes, and if it's still a small number, we might even go to seconds, right? But the point is, you don't have to unless it tells you to. And if you do and it doesn't tell you to, as long as you did it correctly, that's okay. All right? Any other questions? Next one. If we run out of time, we'll quickly finish this on Tuesday. A hummingbird averages a speed of about 28 miles per hour. Cool facts, they visit up to 1,000 flowers per day and reach a maximum speed while driving up to 100 miles per hour. Ruby-throated hummingbirds take a 2,000-mile journey when they migrate, including a nonstop trip across the Gulf of Mexico, in which they fly for 18 hours straight. How far is the trip across the Gulf of Mexico? All right, just the Gulf of Mexico. All right. So what are some numbers that matter here that I put down as givens? Karis, give me one. 28. That's how fast we're going, right? 28 miles per hour. And to figure out how far is the unknown? That's my D, right? How far is the distance? And if I have V, I want to know D. I also need to know what? Yes. Time, and that was given 18 hours. That 2,000 mile journey is a total journey. I wasn't asked anything about that, right? Doesn't matter. 1,000 flowers, doesn't matter, right? So if we rearrange V equals D over T properly, solve for D, it's D equals V times T, all right? Because we would multiply the T to the other side, right? Because it's divided by. And when it gets more complex, we'll show the steps, but this is a short equation. That should be pretty easy. So let's plug those in and take 28. Are my units good? Can I plug it in right away? Yes. 28 miles per hour and hours, right? If that was like seconds and that was hours, we'd have to convert something, right? Always check on that. Finishing that off real quick. 28 times 18. And that's going to give me, what did you say, 504? Exactly. What's the unit on it? Careful. It's a D, just miles, right? We all good with that? Okay. We're going to move on to acceleration then on Tuesday, and I'll post the solutions to everything today before the end of the day, yeah.
If you just like, for this, I just like did it in my head. So do you like have to use the equations?
Yes, because it gets more complicated. All through the year from here. Here's the deal. I'm not too picky now, but once we get even a slight bit more complicated with problems, you're going to have to list your givens, because you'll get a point from that on test or quiz. Write down the equation or equations that are necessary. Rearrange those equations algebraically, then plug in. And I know for now a lot of this is easy and you can't do it in your head, but still always try to back up your work, even on the first quiz with this stuff if it's an open-ended one. Because if you do it in your head and make a dumb mistake, you don't have any work to back it up. So if it's a couple point problem, you won't get any credit if you just have the answer. You know what I mean?
Well, like for number 11, I took like 1/10 of a mile took 7.2 seconds. So that means 1 mile took 72 seconds, which is 1.2 mile, or 1.2 minutes.
I want you to try to get used to using equations, because that's what this course is all about.
Okay.
You're going to be using, I know when it's simple, there's ways you can think about it differently in your head, but eventually you're going to have equations with 5 or 6 variables, and we're plugging in, and there's no way you're going to be able to just reason it in your head. Okay? I guess. Well. Yeah. Hurry up. Nah, just go since the bell didn't ring. Oh, shoot.